Hi students. So today we're gonna start D block elements. So my goal is to record small videos like 5 or 10 minutes video, and we will try to cover up everything as per the NCRT as well as the JMain syllabus. So the purpose is to record short videos and to cover up all the concepts briefly. We will not go in detail. We will just briefly understand the concepts thoroughly. Okay, I mean briefly, not thoroughly, because that we generally do in the classes, right? So our sole objective, our sole purpose is to revise the entire concept within such a small span of time, like within 10 or 20 minutes. We have to cover up the whole chapter. This is my goal. Okay, so let's start D block element. So if you see the notes, one more thing, I have written the notes properly, and at the same time I will be sharing these notes on my Google Drive. You can easily download from my drive, from the link that will be mentioned. So your time will be saved, and you just need to solve as many questions as possible. Okay, so now we will start the revision part. Yes, so now we're going to talk about the D block elements, right? Now, D block elements are also known as transition elements. So the first question comes: why the D block elements are specifically called as a D block elements? I mean, why an element will be called as D block element? Because when you write its configuration, kindly listen. When you write its configuration, and if the last electron goes into the D subshell, then the element will be that the element will belong to the D block. For example, and suppose if if the last electron goes into the S subshell, it is a S block. If it goes to the P subshell, it is a P block. If it goes to the D subshell, it's a D block. And if it goes to the F subshell, it's a F block. So that's a concept which we have studied in the periodic table as well. Now the question, why they are called as transition element? They are called as transition element because if you see the periodic table, in the first group, second group, we have alkali metals and alkaline earth metals, which are highly electropositive in nature. And if you see the P block elements further from group 13 to 18, we have non-metals also. So there is a transition. If you see the arrangement of the elements, there is a transition in the chemical and physical properties from left to right, and these elements somewhere resemble between them, between the S block and P block. This is one of the major reasons. That's why they are called as transition element. And one of another reason is that because D orbital electrons, D subshell, D block elements, and the electrons are present in the D subshell, and the electrons keep on like jumping from one D orbital to another D orbital. Basically, it is called as DD transition. It is called as DD transition, which you can see here. D block elements are called as transition elements for two reasons. If you see periodic table, their physical and chemical properties lie between S block and P block. And the second reason is because of DD transition. That's the reason they are called as D block elements. All right, I mean transition elements. Now, a few important things. If you look at zinc, cadmium, and mercury, they are not considered as transition elements because their d orbitals are completely filled. You can see its electronic configuration: 3d10 4s2, means all the electrons are completely, all the orbitals, I'm sorry, all the orbitals are fully filled, completely filled. And that's why they are called as D block, but not as transition element. Hope it's clear, guys. Now, I would like to inform something. Like if you see scandium, titanium, vanadium, these all elements belong to group 3 onwards. So from group 3 to group 12, this zinc belongs to group 12. If you see the periodic table, group 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, like that. Okay. So if you see this part, this is a third period. This is a this all elements belong to the fourth period. These all elements belong to the fifth period. These all elements belong to the sixth period, and these all elements belong to the seventh period. So now the electron goes into the D subshell, that starts with 3D. If you look at this electronic configuration, 3D1, 3D2, 4s2, 3D3, 4s3, and so on. So that's why these elements are called as 3D series, also known as first transition. These will be called as 4D series because the electron goes into the 4D subshell. They are called as second transition elements, second transition series. This will be your third transition series, and this is your fourth transition series. But the thing is, for if you see Rutherfordium onwards, I have written a key point that elements after on and like after 104 atomic number have very short. Basically, they are more radioactive in nature. They are radioactive, means they emit radiations, and when they emit radiations, their half life is very less, like very small. Yeah, I have mentioned also their half life is very short and their data is unknown to us. और इस वजह से we don't talk about their properties as well. That's why in your syllabus, you have to talk about 3D series, you need to talk about 4D series, and you need to talk about the 5D series. This is what. Hope it's clear. Now, if you look at some important thing I have mentioned out, chromium has a spatial electronic configuration that you have to memorize. Okay, important 3D5 4s1, which we have discussed in the periodic table. Copper also 3D10 and 4s1. And if you look at palladium, 4D10 5s0. So these are the exceptional electronic configuration which you are supposed to memorize. Okay. Now, if you look at this part, copper, silver, and gold, they are called as coinage metals because they are used to make coins. This is a small application, you can say, small uh, like term based question you can get, like which of the elements are coinage metals, so you should memorize it. Now, zinc, cadmium, and mercury are not considered as transition element because of the completely filled d orbitals. Now, one important question comes to the picture. When you go further, when you read further, you will get to know that the transition elements show variable oxidation state. Now, what's the answer to this? Because what happens, the 3D and 4S, let's or 5S and 4D, or let's say 6S and 5D, like that. I mean, 3D series, 4D series, and 5D series. So the n minus 1 d subshell and ns subshell, these orbitals are relatively closer energy wise. Energy wise, they are relatively closer, and that's why if you supply a little bit higher energy, you can easily withdraw the electron from s orbital for sure. But apart from that, you can withdraw the electron from its penultimate shell, and which is your d subshell. आप वहां से भी इलेक्ट्रॉन निकाल सकते हैं अगर आपने थोड़ा सा ज्यादा एनर्जी सप्लाई कर दिया. Means these are energies are comparable and relatively the gap is not that huge, and that's why you can easily withdraw the electrons from the d orbitals as well, and that's why they also show variable or multiple oxidation states. ये हमने स्टेटमेंट में बहुत अच्छे से लिखा है, आप इसको याद कर सकते हैं. व्हेन यू राइट द बोर्ड एग्जाम ऑल्सो, वहां पर बहुत हेल्प मिलेगा. ठीक है, अब देखो, if you look at lanthanum, its atomic number is 57. After lanthanum, we have like these elements which lie just here. यहाँ पर ही वो सारे elements exist करते हैं, and these elements are 4f series. The elements are lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, hormium, erbium, thulium, yttrium, lutetium. So these all elements are F block elements. They are as per the electronic configuration, they belong to 4f series, and these elements belong to 5f series. So these are F block elements. We will discuss its properties later on. Okay, coming to the one important thing, yeah, so we will discuss about the physical properties first of all. So if you look at the physical property, d block elements are solid having crystalline structures due to the presence of strong metallic bond. Yes, the d block elements are very metallic in nature. If you look at iron, cobalt, nickel, and all, their melting point and boiling point depends on the metallic bond strength, and metallic bond strength depends on the number of unpaired electrons. Higher is the number of unpaired electrons, higher will be the metallic bond. Higher is the metallic bond, higher is the metallic and boiling point. तो आपको क्या करना है, आपको इलेक्ट्रॉनिक कॉन्फ़िगरेशन लिखना है. स्कैंडियम का हो जाएगा 3d1 4s2, and eventually if you move further, you will see chromium is 4s1 3d5. Therefore it will have 6 unpaired electron, whereas zinc will have 0 unpaired because all are paired. So chromium वाले group में we have higher number of unpaired electrons, and that's why its melting and boiling point will be higher because its metallic bond will be higher. You agree to this or not? तो यहाँ पर हमने लिख दिया है वो सारी चीज़ें. मोर नंबर ऑफ अनपेड इलेक्ट्रॉन्स, स्ट्रॉन्ग मेटेलिक बॉन्ड, हाईएस्ट मेल्टिंग एंड बॉइलिंग पॉइंट. जीरो अनपेड इलेक्ट्रॉन, stronger metallic bond. Sorry, I need to erase this part. I need to correct this part. I think by mistake I didn't see weak. Okay, weak metallic bond and least melting and boiling point. Hope it's clear, guys. Okay. Now we will move to another physical property, that will be atomic radii. So what happens when we go across the period? The effective nuclear charge first increases, then it remains same, and then it decreases. Why? Because let's say 3d1, 3d2, 3d3, 3d4, 3d5, you are like continuously increasing one unpaired electron in different d orbitals. At the same time, the number of protons are also increasing, so the effective nuclear charge is more. बट आयरन के बाद से आप पेयरिंग करना शुरू कर देते हो. आप लिखते हो 4s2 3d6, cobalt 4s2 3d7, nickel 4s2 3d8. So you start pairing up electrons, and when you start pairing the electrons cause repulsion, and they kind behave like they show better screening effect. तो इफेक्टिव न्यूक्लियर चार्ज लमसम इक्वल हो जाता है, स्क्रीनिंग इफेक्ट के इक्वल हो जाता है. But then when you fill copper and zinc, you are filling up 3d10, means d orbitals are completely paired up. The electron repulsion and the screening effect factor dominates over the effective nuclear charge, and that's why the size further increases. So initially the size will decrease, then the size will remain constant, and the further it will increase. We have already discussed such thing in the periodic table. Apart from that, if you look at down the group, like 3D series, 4D series, and 5D, as we go down, the number of shell increases, so obviously the atomic radii increases. But if you compare with the 5D, यहाँ पर problem आ रहा है because of the poor shielding effect of 4f subshell. Poor shielding effect of 4f subshell. This period, I mean 5D elements, deep 5D elements, they experience a strong nuclear force, or you can say the effective nuclear charge is higher because of the poor shielding effect of 4f subshell, or the same thing is also known as lanthanoid contraction. Because of such factors, the outermost shell or the electron experience a strong nuclear force, and therefore the size shrinks. लेकिन जब नीचे आते हैं तो शेल ऐड होते हैं तो साइज बढ़ता है. यहाँ पर शेल ऐड हो रहे हैं तो साइज बढ़ रहा है, अग्रीड. बट बिकॉज ऑफ इफेक्टिव न्यूक्लियर चार्ज ऑल्सो इंक्रीजिंग, तो उस वजह से दोनों फैक्टर कॉम्पनसेट हो जाता है, एंड दैट्स वाई द साइज ऑफ 5D एलिमेंट्स इज ऑलमोस्ट इक्वल टू 4D एलिमेंट्स. अब एक क्वेश्चन आएगा, तो इसका मतलब स्कैंडियम, इट्रियम, लैंथेनम और एक्टिनम, क्या इसमें साइज डिफरेंस कुछ अलग रहेगा? द आंसर इज नो, बिकॉज यहाँ पर 4f का इफेक्ट नहीं आ रहा है. द 4f इफेक्ट इज नॉट विजिबल हियर, it is not coming to the picture. The 4f things comes over there, so this effect is seen from hafnium onwards. So for scandium, yttrium, lanthanum and actinium, if you go down the group, the shell increases and hence the size also increases, and that's why I have written this answer. Okay, and I have given answer. In lanthanum, no introduction of 4f subshell and hence no irregular atomic radii. हाँ, लेकिन अगर आपसे पूछा जाए जिंक, कैडमियम, मर्क्यूरी, आप कहोगे जिंक इज स्मॉलर देन कैडमियम एंड कैडमियम इज इक्वल टू मर्क्यूरी. सेम लॉजिक हर जगह लगाओगे. Suppose if I say titanium, you will say titanium is smaller than zirconium, but zirconium and hafnium are almost equal size. ठीक है? These points have been written. You can go through, and this is the answer. When electricity conduction, they are good conductors of electricity. अब ये NCERT का ग्राफ है, आप देखो. Initially, this is your green line is your 3D, the blue color is your 4D, and the red is 5D. You can see blue and red means 4D and 5D is almost overlapping with each other, right? But if you look at the 3D, it's a little smaller. So as you go down, as you go across the period, the size gradually decreases. Then यहाँ पर size lump sum remains equal, and then further the size increases. So the graph will go like this, like this. Okay, guys. So we have discussed all the physical properties briefly In the next segment, we will discuss about its chemical properties. In the third segment, we will discuss about its compounds of the D block elements. And in the fourth lecture, we will see miscellaneous things. जो भी चीजें बची होंगी, we will discuss that. Okay. So hope you would have understood the thing, you would have enjoyed the thing, and if you feel like if you have understood, please share this video among your friends. Try to help your friends also. So that's it. That's all for the session, guys. Thank you very much.